Hello everyone. In this video we're going to go over section 10.4, which involves dependent samples. So if you remember from the previous videos in chapter 10, we've gone through two different scenarios in which we have two sample inference, both of which had independent samples. So we have two populations that we're working with, and subsequently we take a sample from each, hence we have two samples. And in the first scenario that we considered, we had independent samples and we couldn't assume equal variances. In the second example, we had independent samples. The samples had nothing to do with each other, just like the first. But in this case, we could assume equal variances. Okay? And so we could assume equal variances in the second case, and that gained us something. And now we're going to turn to a third scenario where the samples are dependent. Okay, so they no longer are independent, but they're dependent. And that, of course, is going to change our situation just a bit. And so let's get started. So in this dependent samples situation, we're still interested in making inference about the difference between two population means. Okay, and we'll denote them mu1 and mu2. And we're looking at the difference, which we'll call mu subscript d. Okay. And so we have to take samples from the population. We take samples of the same size from two populations that have some similarities or are matched together in some way. So this is different from the other two scenarios. In the other scenarios, I could have different sample sizes, and most likely I did. But in the dependent samples case, I take samples of the same size. And additionally, the two populations that I'm looking at have some similarities or are related in some way. And so what I mean by that, and this is the important part of the crux of what dependent samples comes down to, that the two populations are related in some way. So it could be that I'm taking samples on the same person. And so the populations are the same or similar because they involve the same person in both populations. And so they're matched together some way. So it could be taking samples on the same person. It could be taking samples on possibly twins or people who have some same genetic DNA. If I'm looking at something that would, of course, make a difference if I were looking at different people, so I could have some sort of similar DNA or blood type or whatever. In any of the cases, it is going to be the case that the two populations and hence the two samples are going to be related in some way. Okay? And so a lot of people call this matched pairs design when I'm trying to design an experiment, or together they're matched in some way. So I could match them up beforehand based on similarities in height, weight, who knows what. And so in that sense, they're matched together, and so we have samples which are dependent. Okay, so similarity types. So this is these are what I talked about just a second ago. Observations are taken on the same person. They could be like a pre and post test or a pre and post exam. Observations are taken on twins or similar characteristics. Okay, so just more eloquently what I said before. So what happens when I have dependent samples is that I don't really care, because they're related. I don't really care about the samples separately. I care about the difference of the samples. And so this is different than we had before, because I don't care about the samples separately. I had to in the first case because they were independent. But in this case, I only care about the difference. Okay, so the new sample, I'm going to call x bar sub d, which is x bar 1, the sample mean from sample 1 minus the sample mean from sample 2. Okay, so the assumptions of this instance are that the samples are dependent, okay, and the differenced population is approximately normally distributed. So theoretically, I've been going through here the theoretical differences, but there are also some operational differences about what we're going to do or how we're going to conduct this test. And I made the remark a second ago that I don't care about the two populations separately because they're paired. So what I want to do is take the difference between them and look at the differenced data. Okay? And so actually what we're going to do is we're going to have two different samples of data, and we're going to take the difference of them and do our inference on that differenced sample. So of course, if there's a different sample, then of course then there is a differenced population. And so that's what it means here, that differenced population is approximately normally distributed. Okay, so again, the same sort of assumptions, but we're in a different situation. Okay, so how do we actually do this? Well, for dependent samples, you take the differenced data, like I said before, and you treat it like one single sample. So actually, when we do this, when we do the inference, we're going to do the same one sample methods that we did in chapters 8 and 9 for paired inference. Okay, so we're going to do a one sample t-test or one sample t-interval on the differenced data. We'll see what that means in a second. Okay, sorry. Let's go back here. And so here's a summary of this situation. When we compare means with different samples, you can construct intervals and hypothesis tests via the one sample methods that we saw before. So let's do an example. Suppose that there were 20 students who took a pre and post test. So I had 20 students. Maybe I'm trying to teach them statistics. So they come in, I give them a pre-test to test their knowledge on some skill. I teach a lesson based on that skill, and then after I teach the lesson, I give them a post-test. Okay? Ultimately, I'm often looking for, hopefully, a higher score on the post-test than the pre-test. Okay? That would indicate that they've learned something about that skill. Okay? So that's pretty standard in educational research type stuff. Okay? And so I have 20 students here, 1 through 20, their pre-module score, which is the pre-test, and their post-module score, the post-test. Okay? At the 5% significance level, can we conclude that the students knew more after learning the skill? Okay? And so let's write this out. So we could start with the parameter of interest, and the parameter of interest for this specific problem is mu sub d, the mean difference between pre and post-test scores. Sorry for my terrible handwriting. So that's our actual parameter that we're interested in. No longer mu1 minus mu2. And I know that actually seems weird because we defined mu sub d as mu1 minus mu2. Okay, but there are some theoretical differences, even though it looks operationally the same. So the null hypothesis for a paired t-test is what we're going to call it, is the difference. Actually, we're going to change this around. I'm going to call mu d. No, actually, I'm sorry. We'll stick mu1 minus mu2. The hypothesized, the null hypothesis, is that the difference is equal to 0. So just like everything else before, the null hypothesis for a two-sample inference procedure is going to be that there is no difference, that the difference is 0. Okay, and then the the alternative hypothesis is that the difference is going to be less than 0. Okay, if we do, we'll call pre-module mu1 and post-module mu2, I'm hoping that mu2 is going to be larger than mu1. Yes? And so if the post-module score is larger, then the average difference is going to be negative. So I'm looking to see if the difference is less than 0. Okay? Then typical third step, alpha equals 0.05. That's our significance level. The assumptions, data taken randomly. Now that has some different interpretation in this situation. I just didn't go out from the population and take different students for both mu1 and mu2. They were actually paired, but the data, the randomness part has to come in the differenced data. Okay, the differenced part, and so it's viewing the students as different. As random in how I selected them. Okay, don't worry about that which two part. It's always there. Data is taken randomly. The samples are dependent. That's pretty clear because there are measurements on the same student. Okay, and so that's pretty dependent. So we can say yes, and then lastly, the differenced population is normally distributed, approximately. Okay, and so those are the assumptions. Okay, the test statistic, and this is where it gets weird or different from the other two situations, is that the test statistic is the same as the test statistic for a one sample inference, but it's on the differenced data. And what I mean by the differenced data is I take literally mu1 minus mu2 and I find the difference. So if we go over, and I'll turn this to blue, and we look at the difference, I create another column theoretically and operationally, and I literally do score, pre-module score minus post-module score. So 18 minus 22 is negative 4. 21 minus 25, negative 4. 16 minus 17, negative 1. 22 minus 24, negative 2. So on and so forth, all the way down. Okay? And then I do my inference on that differenced data. Okay, so that's the actual data. I don't care about this and I don't care about this. I only care about that differenced column. And so my test statistic is what we usually had before, x bar, but now I put a subscript d on it. It's the mean of the difference minus the hypothesized mean, which is 0, over S sub d, which is the sample standard deviation of the differenced column, divided by the square root of n, where n is the number of students. They both have the same sample size, both samples, and so however many there are is n, of course. So that is x bar sub d, whatever that is, divided by s sub d, divided by the square root of 20 in this case. Okay, and then based on that test statistic, we find the p-value, and then we make a decision and conclusion. Okay, but of course we need Minitab to do all the calculations for us. So let's go look at Minitab. Actually, I was playing around with this already. And so I'll get rid of all of this. I made 2 columns here, and I put all 20 numbers in, pre and post. Okay. So all 20. If I go down here, all 20. And so to do 2-sample inference, whether it's a confidence interval or hypothesis test, we go to Stat, Basic Statistics, and then Paired T. So when I have dependent samples, it's called a paired t-test or a paired t-interval. So I go to Paired T. Okay. And then sample 1, we're going to call pre. Sample 2, we're going to call post. We go to options. Hypothesized difference is 0. And we're looking at a difference of less than the hypothesized difference. Okay. So we could also choose graphs, but I'm not really interested in those right now. We click OK, and we get descriptive statistics on both. So we get them for the pre and post, but we have an estimation for the pair difference. It gives us what's called a one-sided confidence interval, but if we go down here, we get a t-value. Our t statistics would be negative 3.23, and let's see if I can sort of zoom in here. So our t statistic is negative 3.23. That corresponds to a p-value of 0.002. That p-value is less than the alpha level of 0.05. So we reject the null hypothesis, and we can conclude at a 5% significance level that the average, really that the difference data, or the mean, the true mean of the differenced population is less than 0, which corresponds to students learned something on the test operationally. Okay? And I'll go back here. That's what the conclusion was here. At the 5% significance level, can we conclude that the students knew more after learning the skill? Yes, we can operationally. Okay? Based on what I just said. So, as a example here, here's your turn. Okay, a teacher randomly selects 10 students to participate in a week of training designed to improve their typing speed. The teacher begins a pre and post test, okay, to see if their course is worth the time and expense. Here's the data. So you have before and after scores. It's just like our last example. Okay, I want you to perform a confidence interval and hypothesis test for this data. So I want a 95% confidence interval for the difference. And we'll talk about this in class since I didn't go over a confidence interval example. And part 2, at a 5% significance level, can you conclude that the course was worth it? Okay, so try to make that decision with a hypothesis test. And so that's what I want you to do for this your turn. Okay, and that's the end of chapter 10.